less than 10(6), conditional probability. So we're looking at the probability of some event given that another event already occurred. So if you have event A and event B, and you want to know, we'll look at this notation here. So how you get this is the probability that B happens given that A happened. Right? Well, okay. Well, if you know that A happened, it really narrows down the situation to you're somewhere inside the circle, which includes part of B. Right? Okay, so another way to look at this in the Venn diagram, I think is a really good visual, is that probability of B given that A did happen is the probability of A and B happening. That's what this is, this and. Right? So basically this wedge here, divided by the probability that A happened, which is this entire circle, including that wedge. Right, and I think that makes a lot more sense. Okay, so, okay, this notation, and then here I spelled out the word, so I'll say it again. This is probability of B happening given that A did happen. Okay, so we know A happened. What's the probability that B also happened? What's the probability of A and B happening divided by the probability of just A happening? Okay. Again, I would look at the Venn diagram and then that's where to me it clicks and makes sense. Okay. There's a really similar example right here where they're rolling dice over and over. So we got two dice. It looks like they have a purple die and a white die, right? And they roll these, right? So purple and white. Okay. And just glancing, it looks like they have possibly every outcome listed that you could have, right? And they have Venn diagram. So one of the dice being a 5 is in this green circle. The sum is equal to 7 is in this blue circle. Okay. And then, of course, there are a bunch of die rolls you can do that a 5 doesn't show up and they also don't add up to 7. And those are all listed out here. Okay. So here's your universe of dice rolling. Okay. Now, there is some overlap between rolling a 5 and summing to 7, right? Either roll a 2 and a 5 or a 5 and a 2. So if they ask the question, what's the probability? Um, how do they phrase this? Okay, so event A is rolling a 5 and event B is rolling a 7. Okay, so what's the probability of rolling a 7 given that a 5 was rolled? Right, so you know at least one of the dice is a 5. You know that for sure because that's been given already. Okay. But what's the probability that the two dice do in fact add up to 7? Right? Well, there are two ways that they could add up to 7 with a 5 being rolled, either the 5 and the 2 or the 2 and 5. Okay. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different ways to roll a 5, or that 5 was rolled. Okay. So it'd be 2 out of 11. So there you go. Okay, so 2 out of 11. Okay, so conditional probability, the probability that some of it happens given that something else is known. All right, so let's jump into some book examples here. Got it. Example 1, conditional probability. Example 1. There are currently 16 customers in line at the deli counter, each holding a ticket from 179 to 194. 179 to 194. Right. You could list these all out. I might do that. Naveen will be helping customers with even numbers, and Ellie will be helping customers with odd numbers. Right? Now, one thing to notice is that there's an equal number of tickets. I see an even number because we started on an odd and we ended on an even. So there's the same number of odd tickets as there are even tickets. So if a customer is helped by Naveen, who is helping with the even numbers, what's the probability that the ticket is 190? So number 190. Right? Well, let's look up the sample space. Here, I'm going to spell it. So sample space, right, for event A. And event A is you're helped by Naveen, hence you would have an even number. That could be the number, ticket number 180, 182, 184, 186, 188, 190, 92. There you go. And 194. Okay. So Naveen is helping out the customers specifically with this list of tickets. So it looks like 8 people here, 8 people. Okay. Okay. So they phrase this, what's the probability that the customer is holding ticket number 190? Okay. So there's only one ticket 190. So probability of the number 190, I guess that could be event B, couldn't it? Event B. Okay. Given that you are helped by Naveen, which means you have one of these 8 tickets, that'd be 1 out of 8. So there you go. So 1 out of 8. All right, and there could be different ways to approach that, but you get it. All right, example two, interdependence using conditional probability. Researchers surveyed workers at a tech company about their education levels and income. The two-way frequency table shows the workers who responded. And so we have different incomes. Let's try to put this on screen here. Okay, we got these different income categories, 35,000 to 50,000, let's call it, 50,000 to 65,000, 65,000 and over, three. Right? And then also these degree categories, master's degree, and then total. Um, Consider a worker is chosen at random. Are the events of a worker having an annual salary over 65,000 and having a master's degree, are those independent events? All right, well, if you look at the numbers here, looks like if you have a bachelor's degree, there are a lot of workers with like low incomes with bachelor's degrees. But if you go over to the column with master's degree, ooh, it looks like the salaries jumped way up. Right now, there's a lot of high type salaries. Right? So my gut instinct is that having a high salary is not independent of the degree you have. If you have the master's degree, that will be correlated with having a higher salary. Right? Now there has to be a way we should be able to define this. Where'd it go? I saw it. Um, Probability. I see it. It's right here. It's right here. It's this little blip. Okay. So if events A and B are independent of each other, that means that the probability of A given B is the probability of A. It's the same thing. So I'll write this down. Okay. So if events are independent, then the probability of A happening given that B happened is the exact same thing as the probability of event A happening just in general. Okay? It doesn't matter whether B happened or not. And you can also go the other way because they list the vice versa here. They say, well, the probability that event B happens given that event A happened, well, that's just the same thing as the probability that B happened in general. It doesn't matter whether A happened or not. That would indicate independent events. Independent events. Okay? All right, so again, I think that's not the case here. So how can we show that mathematically? So example two here. Okay. Um, so I'll list event A as salary. Did they say over 65? Yeah, over $65,000. And let's have event B be you have a master's degree. Okay. Right, so what's the probability? Let's try it this way first. Right, of A given B. Okay, of A given B. What would that be? Okay. Well, if I give you B, then now we're only focused on master's degrees. So that's this whole column right here. And then $65,000 or more, that's 39 out of 62. Okay. So there's 62 people with master's degrees, and 39 of them have a very high salary. So that's 39 out of 62. Okay. And if I like, I could turn that into a decimal or a percentage, 39 out of 62. That's called 0.629 or 62.9%. Okay. Now, what's the probability of just earning over $65,000, which is just an A itself? Okay. Because again, if these match, if I get the conditional probability and just the regular probability are the same, then I can say, oh, well, these events are independent, earning the salary has nothing to do with what degree you have, blah, blah, blah. Okay? But my hunch is that these are going to be different values, so these are not going to be independent. And so what's the probability of having a very high salary? Well, there are 42 people with this very high salary out of 100 people altogether of the company who were surveyed. So that'd be 42 have a high salary out of 100. As a decimal, it's called 0.42, or as a percentage, 42%. Okay, yeah, this and this are not the same at all. It looks like if you're just a person at random, you have a really high salary, 42%. But given that you have a master's degree, now the chance you have a high salary jumps way up. Yeah, that's what we were kind of saying that before. And I was looking at just the table values, right? Looking at forest for the trees. Like, okay, yeah, I think that would be the case. Okay. Now we could also analyze this the other way too. Instead of this condition, what if we did it this way? Okay. So what's the probability of, see, B given A? That would be having masters given that you have a very high salary. Right. So we're looking at the same 39 people, but this time it's out of 42. So 39 out of the 42 people with a high salary have the masters. So this is 39 out of 42, right? Which is almost everybody that has the high salary would have a master's. I'll call it 0.928 or 92.8%. Okay. So over 90% of the high salaries are people who have master's degrees. Okay. Well, what's the probability of simply having a master's degree? There's 42 of these. No, sorry, that's not right. Sorry, there's 62 people with masters out of 100. Okay, so 62 out of 100, or 0.62, or 62%. Okay. Okay. So the people with masters at the companies account for 62% of the employees, but over 90% of the high salaries. There you go. Again, the fact that these are not the same, and of course, these were never going to be the same because they weren't up here either. These are not independent events. Having a high degree and having a high salary are not independent. You say those are dependent on each other. If you have a high degree, that's correlated with a higher salary. All right, let's jump into some puzzles. Got some highlighted here. Number 3, game. In a game, a spinner with 7 colors, so the rainbow is spun. Find the probability that the color is blue, given that the color is one of the 3 primary colors, red, yellow, or blue. So draw this out. Got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There you go, 6, 7. Okay, let's make believe those are all the same size wedge. Okay? Now one of these is red, one of these is yellow, and one of these is blue. Okay? So I'll call event A being blue. Let's call event B being primary color. Okay? Now, just to do a little overkill on this, the probability of event A would be 1 out of 7. So if you just keep spinning this all day and getting random wedges, 1 out of 7 times it'll be blue. Okay? The probability of one of the primary colors, which is event B, well, it's 3 out of the 7 wedges. Okay? Now, what is the probability of um, event A given event B? Okay, so we spin this. Maybe you're blindfolded, and I tell you, oh, I'm not going to tell you what color it is, but I will tell you it's one of the primary colors. Say, okay, and you're thinking, huh, what's the chance that it's blue? Okay, well, it's 1 blue out of 3 that it could have landed on because I narrowed it down for you. So the answer has to be 1 and 3. Okay. Now, what's another way we could have looked at this? Here we go back to the beginning, because I told you another way is we could look at it like this. Okay, so probability of A given B, okay, could be the probability of A and B happening, which would happen 1 out of 7 times. I mean, if you pick blue, it will also be primary, so it's 1 out of 7 times. Okay, and then probability of event A, which is oops, sorry, did I get that wrong? 3 out of 7. There's probably event B, A and B. Event A, it's blue. A and B happening. Okay, I see what I'm confused. Okay, because in my original notes I have B given A, but I'm doing A given B. So my A and B is swapped here. Okay, so event B a primary color, that's gonna happen 3 out of 7 times. Okay, now we're good. We're back on track. Okay, if you divide this out, 1 over 7 divided by 3 over 7 is not the same thing as 1 over 7 times 7 over 3. The 7s cancel, leaves you with 1 over 3, which is the exact same thing. Okay, so using this page of notes that you saw at the very opening of the video, you get 1 and 3. right? Or if you just consider it this other way, it's 1 and 3 no matter how you look at it. 1 and 3. So we got that. Number 5, picnic. School picnic offers hamburgers, hot dogs, chips, and a drink. At the picnic, 60% of students order hamburger, 48% get a hamburger and chips. Okay. So let's get a Venn diagram going here. Okay. So there's all these students at this picnic. Okay. And there's all these food choices. Got hamburgers, hot dogs, chips, drink. Okay. So I'm gonna make one bubble and I'll call this hamburgers. Hamburgers. I'll make another bubble and I'll call it chips because it looks like chips are also showing up. Let's do chips here. Okay. And here's, of course, all students. All right, so we've got all these students. Okay. And now it's kind of percentages. If you want to, you could think about that being like 100 students and just put numbers. I'll go and do percentages. So 60% hamburger and 48% hamburger and chips. Okay. So, well, if I'm just focused on hamburger and chips and anything otherwise, I know in this wedge I'll put 48%. So let's put 48% as hamburger and chips. Okay. And I said 60% is only hamburger. So that must be the other 12%, doesn't it? Because now those add up to 60%. So I think this is as much as my Venn diagram as I know so far. Okay, I just know that. Okay. Well, I know the whole thing has to add up to 100. So I know all that. All right, next statement here. 50% of all the students ordered chips. Oh, well, if 50% of all the students ordered chips, then I've almost accounted for everybody, but it looks like there's another 2% who ordered chips, but not hamburgers, because that would create 50% ordered chips. Okay. Then, are the events of ordering a hamburger and ordering chips independent? Justify your reasoning. Okay. So it's a question about independence. Okay. Now, I think the answer is no, because I think, yeah, there's a high correlation between ordering one and the other. Okay. If you get hamburger or chips, you're very, very likely to also get the other. Okay. Okay. But how can we show that mathematically? Well, that's going to go back to this right here. So the probability of A given B, the same thing as just probability of A. And B given A, the same thing as probability of B. Because if that was the case, they would be independent, and if it's not, then it's not. So let's do event A equals got a hamburger. Let's call event B, you get chips. Okay. So probability of A is hamburger, would be 60%. Probability of see A given B, yeah, right. A given B. Okay. Okay. Probability of getting a hamburger given that you got chips. Okay. Well, out of chips, there's total of 50%. And 48 out of those 50. So it'd be 48% out of the 50%. Who got chips also got a hamburger. Okay. That's gonna simplify to 96%. Okay. Yeah, the fact that these are not the same, so not equal, means that these are not independent events. Talking about events A and B, which is hamburger and chips. Okay. So here I showed, okay. So reiterate this. Okay. If I know that you got chips, then the probability that you also got a hamburger is overwhelmingly likely. Right? If you have chips on your plate, 96% of the time you also have a hamburger. Okay. But the probability of, if I look at all the students at this picnic, probability that you have a hamburger in general, okay, it's a little over half. It's about 60%. Okay. Yeah, these are not the same number. They're not anywhere close. So these are not independent events. And I could go the other way too. I could go with chips given that you got a hamburger and so on. Right? They would also not be equal. Right, so pretty good there. Let's do one more here. Got a Venn diagram of students' favorite places to go. Got library or home. So number 11. All right, first, let's copy that diagram so we know what we're looking at. Okay, so got library or home. Where do you want to study? Okay. It looks like 12 students study strictly at the library, 36 strictly at home. And I got these 6 students that, okay, some at the library, some at home. They're flexible. Okay, total 60 surveyed. Do these add up to 60? Can I add plus 12, 6, and 36? What? That's only 54. Oh. Looks like we must have some students who are not studying at all. So let's make a wider universe here. And there's 6 students who are not studying. So we just found. Determine the number of students who replied that they study neither at the library or, actually, that was question A. So we just answered question A, which is 6. We just got that. Okay, question B, what's the probability that if a student selected the library, which is now narrowed down to these 18 students, okay, so we're given that event, uh, that he or she selected studied the library and at home. Okay, so let's call event A equals library and B we'll call home. Okay. So we want to know what's the probability of studying at home given that you study at the library. Okay. And it looks like there are 6 students who do both out of 18 students that study the library in general. I think that reduces to 1 and 3, doesn't it? Or 33%. Like that. And what else? Your classmate says that selecting the library and selecting at home are independent events. Do you agree? Ooh, well, if they were independent, then B given A would be the same thing as probability of B. So what is the probability of B, which is studying at home? Now let's see, because if this is also 33%, then maybe the student's right. And if it's nowhere near 33%, we know they're definitely wrong. Let's see, or is there some kind of correlation? So on. Okay. So studying at home, that looks like what, 42 students? Or okay, we've got 42 studying at home out of 60 altogether. So what is 42 out of 60? That reduces to 70%. Okay. Now, if I'm comparing this 33% and the 70%, those are definitely not equal to each other. So just to recap this so far, looks like 70% of all the students are studying at home. Yeah, maybe also the library. Right? I'm not discluding those, right? But 70% are doing some home study. Okay? But if you're given that they do study at the library, the chance that they also want to study at home is much, much less. In fact, it's about half as much. Okay. So if you see some students studying at the library, are they also studying at home? Well, okay, a few are, but proportionally speaking, much, much smaller than just everybody studying at home or in general. Okay. So for that reason, I would say these are not independent events. Events A and B, studying library, studying home. Okay. So once you know that somebody studies in one place, you say, okay, well, they're maybe not as likely to study at the other place. All right, there you go. Conditional probability.